All right, in this video, I'm going to actually do homework one in engineering format the way that I would want you to submit homework. I'm finding it's difficult to make sure everyone's on the same page. So if I do homework one, that's what I want. Okay. Now, there are reasons why I am making you do engineering format. It will help you in the long run. All right. Making you do Excel. You will use Excel many times in your life. And if you don't have the proper stuff, if you ever need to go back to that Excel sheet, you're going to forget what you put in there. All right. So um, I'm doing it on engineering paper in pencil. That's what I want. And typically up here in the boxes, I want your name. Okay. You can put today's date. You can put the course, which is ENGS 314. And then just put fluid mechanics. And then over here, homework number one. And I'm going to do problem 1 and 2 on this. Okay. So name, date, the course, the homework number, and the problems. Okay. Typically, you only do one problem per page, but because there's no engineering format, you could put that on the page. Okay. So just start. Problem number 1. And I'm using a straight edge and I'm just going to underline it. Okay. Practice your handwriting. Being organized, neat, and making sure you write clearly is key. Okay. So problem 1 in homework 1 is a pump is used to transport water to a higher reservoir. If the water temperature is 20 degrees C, determine the lowest pressure that can exist in the pump without cavitation. Okay. So there's just a chart that I provided you in the lecture notes and in the homework video help. 20 degrees, 2.3. So PSAT 2.3. Oh, so I use pencil so you can erase. 3, 4 kilopascals. Okay. And then I would box your answer. Okay. Box your answer. All right. Problem 2. You can do it right here because the first one isn't engineering format. Now, bare minimum. Okay. I want given. Let's put find right here. Sketch. And then you will have solution down here. Okay. Right now, we could put assumptions, but I'm going to wait. Okay. When you do start doing Bernoulli's, that's when I want assumptions. Okay. So given, so let me read this. So you have compare the Mach number of air, which has an R value of 287 joules per kilogram K, from 350 degrees C, 350 to 700 degrees Fahrenheit, which is moving with a velocity of 900 feet per second. Use K equals 1.3. Make sure to provide at least 3 sample calcs. Okay, so first thing is R, 287 with units, joules per kilogram K. And I'm just going to move find just slightly over to the right. Okay. We have temperature from 350 to 700 degrees Fahrenheit. Velocity is 900 feet per second. K is 1.3. And we're going to find a plot. And I'm just going to put what the plot here is. You want to find Mach number versus temperature. Okay. And what do we have? What is it? The plot of Mach number. Oh, I didn't specify. So let's just do an airplane. Something like that. Okay. Very simple, but there's a sketch. Okay. So given, find, sketch, and then right here, solution. Okay. With a heading. So here would be what? Mach number. M equals V over C. Mach number is V over the square root of KRT. Okay. So you have, and then it wants 3 sample calcs. So sample 1, underline, sample 2, underline, sample 3, underline. Oh, let's do T at 350 degrees Fahrenheit. T at, let's do 500 degree Fahrenheit. And T at what? 700. So at the start, the middle, and the end. Okay. So we have V, we have K, we have R, but T you got to convert. And you can convert it right there. Let me see. I can't remember conversions off my head. So we can go back to the notes. Actually, I'm just going to go to my notes and look here real quick. Hold on. Okay, temperature. So you can look online or look at my notes. Let's see. So we're going to go with to Kelvin. All right. Let me move this over here. Move my paper up for you. So it's going to be 350. Oops. Let's write the main equation first. Which would be TF minus 32 times 5/9 plus 273. Okay. So TK 350 minus 32 times 5/9 plus 273. Okay. Over here, I can draw a line straight down. TK is 500 minus 32 times 5/9 plus 273. And then TK here is 700 minus 32 times 5/9 plus 273. I'm going to move that right there. Okay. Calculator. I think I have one somewhere. I'll just use my phone right now. But I will. I know I have a calculator. Give me a second. Not sure where it went. Well, plug that in. So 350 minus 32 times 5 divided by 9 plus 273. So 450 roughly. Kelvin. Because you got to convert it to Kelvin because this temperature has to be in Kelvin because these units are Kelvin. Okay. Now, before I continue, you can convert this. You can go ahead and write what that is. That needs to be in meters per second. Okay. So what do we have? 900 feet per second to meters per second. So 274. 274 meters per second. I'm okay right now if you just write that. Okay. All right. So go back to the temperatures. And I'm just going to, I did one calculation. I'm just going to convert these. So 500 F to K, 533 Kelvin. And what's the last one? 700. 644 Kelvin. Okay. Okay, and then I'm just going to put now Mach number is 274 meters per second over square root of 1.3 times 287 joules per kilogram K times 450. Okay, that is a terrible, see, that's why we use pencil. It needs to be the square root of all of that. Okay, and the Mach number becomes, let's see, so 459, about 0.51. Okay, Mach number 274 meters per second divided by the square root of 1.3 times 287 joules per kilogram K times 533. The Mach number becomes, oops, what temperature are we at? 500. 0.47. Okay. And the last sample calc, 274 meters per second divided by square root of 1.3 times 287 joules per kilogram K times 644 Kelvin. Oops, I forgot the units on the temperatures here. Mach number becomes 0.42. And then I would box these. Okay, so let me just zoom right there for problem 2. So this would be what I would expect for the first part of problem 2. You have your givens, you have find, sketch, solution, heading, equations in your sample calcs. Okay. This is what I want for hand calcs. Then for the Excel, let me see here. Shoot this over. This is what I want for your Excel sheet. Okay. What you have is the heading right here that has your name, the email, the date, your school, your class, the class number, homework, and your description. Okay. You can copy and paste this. One time you do it, you can copy and paste. Problem number. Okay. Then write your givens with the units. Okay. These are the numbers. And then what you're looking for. Okay. Then scroll down. Here is my table, temperature in Fahrenheit, temperature. This is the conversion factor. Okay. This is my speed of sound equation. And then here's my Mach number. So I have 1, 2, 3, 4 columns. And if you notice, these are hard numbers here because I put them in. These are conversions based on this value. Okay. And same with the speed of sound. Those are equations that you need to put in and the Mach number. And then here is your graph with the title, with the Mach number over here and your temperature over here. And then this is the line. So you would email me this Excel sheet, okay? Again, this is a good way of practicing your Excel skills, which you will use in your lifetime heavily. So this is problem 2. Let me go back to, I think it was this. Yep. Okay. Now, up here, because we're going to another page, this is going to be 1 slash. This bottom is your total number of pages. Now on the next page, I would put at least your name and the homework, because what happens if you had it stapled? Homework 1, this would be problem number 3. If you stapled it, the staple goes right here, okay? The top left corner. If for some reason it got unstapled, you would know. So this would be 2 out of whatever. Okay. Okay, so problem 3 now is this block that goes up the incline. So start with givens. We have a 50 centimeter by 30 by 20. Okay, so we can do length 50 centimeters, height is 30 centimeters, and the width 20 centimeters. Weighing 150. So let's do FW, sure, is 150 newtons. That right there. So we got constant velocity of 0.8 meters per second. Coefficient of friction is 0.72, or sorry, 0.27. And I'm going to put find right here. We're looking for F and percent reduction. Okay. Givens, find bare minimum. Here's our sketch. And I would label this A. This is where you should use a straight edge. Okay. It's at some angle. All right. And then you make the box, and you can draw the forces. You may want to draw the forces in colored pencils. FW, this is going up the ramp at constant speed, so the friction is backwards. You have the normal force, which is perpendicular to this. Let's put the axes on here, X and Y. And then we have F. Okay. I'm actually going to move this. Call this FW. Because we're going to break this up into Fy and Fx. We're going to break this up into components. This is theta. That's theta. This would be Fwy and Fwx. Okay. Now I have a whole video on this sketch, so I will make sure to link that video in the description. So again, this is page 2. Start the new problem on a new page. You have given, find, sketch. Okay. Now, if you want to draw part B with the liquid layer, you can, but you could just put liquid layer if you want. Okay. Just to make it simple, because we know there's going to be a liquid layer here. So again, given, find, sketch, bare minimum. And then we can start the solution down here. You need to have these. You can't just give me equations and without like plug numbers. You have to tell me the givens, the find in your sketch, because you can't do this problem without the sketch, because there's forces. I would put newtons second law. Underline it. And I'll zoom in a little bit more on this case. Okay. Now we have two directions. So X direction, Y direction. And while I do that, I'm going to keep that here because I know I did this in another video. And so I'm going to just go to it to make sure I don't miss anything. Perfect, right there. Okay. So we have a heading, X direction, and I know I'll just put a line here. And we got to pick a direction for the X and in the Y. So we have sum of the forces in the X equals MAX. Underline it. Sum of the forces in the Y equals MAY. Underline it. We have minus friction plus F of X minus WX equals 0. In the Y, we have the normal force. I think we didn't call it W, we called it FW, didn't we? FWX. Again, that's why I use pencil. We have normal minus FWY minus F of Y equals 0. Then, if you want, I'm okay up here if you put a note. You put friction is mu N, fun, and then friction force would be mu A, what was it? Delta V over delta Y. Okay, just for you to have a note, or you can put it over here. Okay. So part A, I can put part A right here, minus mu N plus F cosine theta minus FW sine theta. Over here we have the normal minus W cosine theta minus F sine, that's FY, FW. F sine theta equals 0. And then I believe I solved for the normal force, which is FW cosine theta plus F sine theta. And then you can put an arrow. And then you can plug that in. Minus mu FW cosine theta plus F sine theta plus F cosine theta minus FW sine theta. This one equals 0. Equals 0. Now you see how that line is in the way? I'm okay if you leave it. I would maybe erase it. I might as well use a better eraser because it'll look better. So let's fix that. I'll do it right here. Perfect. Okay. And then you can keep going. Okay. Honestly, for part A, for this one, if you show me to here without plugging numbers, like, I'm okay. Why? Because I'm making sure you understand a physics background, because we're going to be doing forces when we do hydrostatic forces. Okay. So, and then part B, you do the same thing. Sum of the forces in the X equals MAX. And then sum of the forces in the Y equals MAY. And we forgot to do this on part A, but those are 0, right? Because they're not, it's moving constant up the ramp. And then fill it in. But the only difference is, again, up here, the friction force is different. So let me zoom out. I don't know if it's not getting everything. So there we go. Perfect. Okay. Now, again, this is problem 3. Problem 3, where you have the incline. You can't just give me these equations here. Okay, you can't just show me this with numbers. You need to show me your givens, okay, your sketch, what you're looking for, then write solution underneath this, write a heading, and write your Newton's second law with the forces. Okay, go down the page, please. Okay, there are a lot of you in this class, and if you don't do it this way, it's really hard for me to look at and see what you're doing. Okay, this is the standard that I want. Okay, I will email you back if you're okay. All right, if you've given me something, I may have a few that I need to email. You might see this before I send it back, but I will send it back whatever I got today. So look, this is problem 1 and 2. Look at nice and neat down the page. Then you have the Excel sheet for problem 2. And then you have this for problem 3. Okay? Bare minimum, given, sketch, find, solution with headings. Okay? Now, we're on to the last problem, problem 4. So, I'll zoom back in a little. Let's see better. So again, put your name and then homework number 1. This is problem number 4. Now, some of you, which is totally fine, are writing this on your tablet or other things. You don't have to. I'm okay if you don't use engineering paper and scan it in. You can use it on your tablet, okay? Just be very clear that it's problem 1 and make sure you have given, sketch, find, and solution, okay, underneath those. So this would be 3/. Okay. Technically, the Excel sheet would be page 3, but you can, like if you ever needed to hand it in, I would put maybe 2A, all right, to indicate, okay, it goes with this page. And I usually, what I would do is page 1, then the Excel sheet, and then this problem. So like I like when people staple the Excel right after the problem, not at the end. Okay, we're on this last one, which is in the falling ball viscometer, a steel ball is 1.6 millimeter in diameter. It's allowed to fall, having a specific gravity of 0.94. Steel weighs 77 kilonewtons per meter cubed. The ball is observed to fall 250 millimeters in 10.4 seconds. Calculate the viscosity of the oil. Okay, now, say you're like, okay, I'm stuck. Well, you can go to the video help or the lecture. So I'm just going to grab, let's see, where is it? See video. Okay, so in my video help for this problem, it says see video example. I wonder if I've done this problem. I might have. So let me bring up this playlist view. Let's see. Oh, look at that. Falling ball viscometer example right here. I'm just going to pause it. Oh, wow. Is it the same? 1.6. Awesome. I'm going to do it again, but I also have this video, entire video, exactly how I wanted this done in the playlist. Okay. So, given, like I've already done this problem, D equals 1.6 millimeters. Let's convert that. 1 meter, there's 1,000 millimeters. Okay, so you can bring that over 3 places. 0.1216 meters. SG 0.94. Delta S 250 millimeters. And the time 10.4 seconds. Find mu. And we have a sketch. So here's this falling ball viscometer. Here's the ball. This distance is delta S. Okay. And if you want, you could do a free body diagram on here. I think we have what? Drag and I believe weight, right? Now, I do want to note sketches. Don't make them so tiny I can't see or you can't see or you can't do stuff. This is a good sketch size-wise. Now, in that video, I did have assumptions, but we don't need to because this is the bare minimum. The ball reached terminal velocity, which is key, and the ball isn't spinning. All right. Cool. Where is my mouse here? There it is. Okay. Let's see. What do we have right there? Okay. Solution. Start right here. Heading. Viscosity. Equation for falling ball. Okay. Heading underline mu equals delta S, not delta, sorry, gamma S minus gamma F times D squared over 18 times V. In this, we need to find velocity, right? V equals delta S over delta T. All right, and if you want, we can change this to delta T in the givens. V equals 250 millimeters over 10.4 seconds. We're going to convert this 1 meter. There's 1,000 millimeters, right? Now V is equal to, I already have it done, 0.024 meters per second. Okay. Now again, given, find, sketch, solution, heading, main equation without plugging numbers in, and then tell me in this, okay, what am I looking for? I'm finding the velocity. Boom. Find it with units. Go down the page, please. All right. Now we need to find gamma F, right? Gamma F is rho F times G. Gamma F equals SG times rho W times G. And let's go ahead and plug 0.94 times 1,000 kilograms per meter cubed times 9.81 meters per second squared. Okay, and we get gamma F is 9221. And in the video, I showed some unit stuff. Newton over meter cubed. Cool. Okay, and I think we did forget in the givens gamma what? S, which is 77 kilonewtons per meter cubed, and I converted that to 77,000 Newton over meter cubed. I did that on purpose to show you some values, okay? Let's see here. Yep. Okay. Now, one thing. See how there's a little bit left? I'm okay if there's a little bit left. You draw an arrow. But the best thing would be to make a new page. This would be homework number 1, problem number 4 continued, and this would be 4. And we know there's going to be 4 pages, so you can put 4 on those. All right, so now we can finish this. Mu equals 77,000 Newton per meter cubed minus 9221 Newton per meter cubed, parentheses, times the diameter squared, 0.0016 meter squared, divided by 18 times 0.024 meters per second. Did I miss anything? Nope. And we end up getting mu of, let me see here, gotta be close. Yep. 0.4 Pascal seconds. Box your answer. Okay. And again, remember, Pascal is a Newton per meter squared. Okay, just note. Now, you don't need to write that. I just wanted to let you know. Okay. Now, in this problem, I have noticed some of you are boxing like these answers. Those are not the final answer. So whatever you're looking for, that's what you box. Okay. So box that one. Okay, you don't need to box anything else because it distracts me, honestly. Okay. So look at, we would have 5 pages in this. Problem 1, problem 2, problem 3, problem 4, and then after problem 2, you have an Excel sheet between this page and this page. Okay. But if you're sending it to me electronically, then you would send these 4 pages, okay, and then send me the Excel sheet. I hope this helps. Again, I'm seeing a lot of students just say problem 3 and they give me like this equation. That's not going to work. Nope. Because again, I'm trying to teach you not only the content, but to be organized, to be neat, to show your work clearly. Because when you do your work and you hand it to your employer, okay, or whoever you're working with, they want to make sure you're doing it right. Okay. That's why I make you do the Excel. So let me go back to the Excel sheet. Where to go? With these headings, right? Why do you think I make you do this and making you do this with this? Because I've been there. Or I did an Excel sheet and I could not remember what I was doing. And it took me probably 3 days to figure it out, and it was important. And I should have had this heading here and the givens and clearly explained what I was looking for. Okay. Now, I know this is 40 minutes. I've pretty much, like, if you do what I just did here, okay, do the Excel sheet. If you haven't done it yet, I did it. Homework 1's done. Okay. Just redo what I did. Okay. Students that have handed me homework 1, I'm probably going to ask you to fix one problem if you didn't do it right in engineering, and then resubmit it, okay? Because they've already attempted to do it. You need to work on this. Homework 2 and so forth, especially when we get to Bernoulli's and pumps. If you don't do it the way that I'm showing you, it's going to be very difficult because there's so many steps, okay? All right. Thank you. Bye now.